In this video, we'll look at section 8 of the Math 121 exam from 2018. We're asked to consider this differential equation, 1 minus x squared minus y squared, and first identify the slope field that matches that differential equation. So the easiest way to do that, I find, is to look at specific points. For instance, if we look here at the point 0, 1, a flat tangent line seems reasonable, or at least close to it. And in this graph, it's a very steep uphill, and this one also might have 0 slope. Let's see what this graph gives us. At the point 0, 1, we're going to get dy dx is equal to 1 minus 0 minus 1, which is 0. Perfect. We've already ruled out this graph because at that specific point, this slope field has a very, very positive slope, very clearly positive slope. We haven't eliminated these two yet. All right, how else can we compare them? What we're doing is scanning the graph for points of difference. I think the easiest point next is at the origin. Here, the slopes are down. Here, the slopes are up. And so which of those matches the formula? We're going to get 1 minus 0 minus 0. Well, that's positive slopes. That only matches this graph here. This graph has a negative slope at the origin. That cannot be coming from that same differential equation. So, perfect. We have found our solution. Our slope field. Now we're going to build our solutions. We're actually starting through the point 0, 1. Well, that's the point we started here. And when we sketch the solutions, we're again just trying to follow the trend line of the slope field. And the key thing is, if you ever touch one of the lines, you have to be going at the same slope as that line. So this cannot be a solution graph, because when we touch this slope line here, the slope's going that way, we're trying to draw a graph going that way. Those are incompatible, so off limits. 1, 0, that's here. So again, just trying to follow the curve as best we can. And we see something like that. So two sort of S-shaped curves would be fine. Now, what we're going to do is use Euler's method with a step size to, starting at 0, 1. Notice that we had a solution here, 0, 1, yes, there we go, to estimate the value of the function of this curve at x equals 2. So what we're going to do is mathematically follow slope lines instead of sketch slope lines to predict what's going to happen a little further on. Now the process here, mechanically, is we're going to be at a point, 0, 1. We're going to follow the slope that we find there for 0.5. We're given that in the question of delta x. Then we're going to recalculate our slope, follow that, recalculate our slope, follow that. If we take 4 steps of 0.5 each, we're going to end up at 2. I find the easiest way to organize this is with a table. We start at x equals 0, y equals 1. We calculate our slope, which is equal to 1 minus x squared minus y squared. And then we figure out the change in y as a result of that. The change in y is just the slope times our delta x. Why is that the case? Because all we've done is rearrange delta y over delta x equals slope to solve for the piece that we don't know, the delta y. All right, so 0, 1, our slope is 1 minus 1, that's going to be 0. That makes this 0. Then what do? We figure out what our new value is by adding the change that we just made. Here we change delta x by 0.5. Here we change y by delta y, but that's just 0. So we end up back where we started, same height. And again, we can see that in the graph. Let me do this in a different color here. Here's 0.5. So at that point, the slope is 0. So we follow a 0 slope, and we end up still at y equals 1. After that, it gets a little more mathematically interesting, or at least calculationally interesting. We have 1 minus x squared minus y squared. Our x is 0.5, 1. If you do the calculations, you end up with negative 0.25. And that means this change in y is going to be that slope, so it's going downhill for step of 0.5. 0.125, half of that. And then we do the same thing again. We add that new value to our delta, add that delta y to our y value. So we'll have 0.875. our x always goes up by 0.5, pardon me. There we go. Our x always goes up by 0.5, so we're at 1. In fact, I'm just going to fill these in. We always know the x step. Then we go back to the next one. Here we have x and y. We have 1 minus x squared. It's going to cancel. And we're going to have minus y squared. So we'll have negative 0.875 squared. That'll be negative 0.76. Do we say how many digits? Usually 3 is fine for these things. 6. And then we multiply that by the step size to get the change in y. 382. 383 if we round. All right. We've already done our delta x. We take that and we add it to our original y, and we are at 0.492. And one last step. Our slope is going to be 1 minus 1.5 squared minus 0.492 squared. That is negative 1.492. And multiply that by 0.5. We get a change in y of negative 0.746. We add that to our 492. And we get negative 0.254. And so we would get y of 2 from this method is approximately negative 0.254. Now we should be able to compare that back to our graph, and you can kind of see how that worked. We took a step here, we took a step down. We're not quite following the graph that we had there because we're taking more linear steps, but here we ended up a little bit above the axis, here we ended up a little bit below. So we're certainly following the general shape of the curve that we sketched out in part A, which is an excellent verification that we're on the right track with this calculation.